The last part of this chapter has to do with carbon exchange at the global scale. Once we understand some of the basics of how carbon is exchanged for terrestrial ecosystems, for lakes, for streams, all of that can be added up to understand the larger patterns that happen at the global scale. Seasonal and latitudinal variations in the carbon dioxide concentration of the atmosphere provide a clear indication of global scale variation of NEE, so of net ecosystem exchange. So we can look at the globe and we can see by measuring CO2 concentrations where there's net release and where there's net gain of CO2. So we can do net ecosystem exchange calculations at the global scale. When these are done, it's essentially a tower that measures CO2 concentrations, just like we saw before with the micrometeorological tower. So at the top, you'll have an air sampler, and that'll measure CO2 concentrations up here. This is the Mon Aloha Tower, which is a couple thousand meters high above sea level and measures CO2 concentrations mostly coming off of the Pacific Ocean. Because we're up high, we don't really care about whether there's movement of air up or down, so we don't need an anemometer. And so in this case, we just want to know what the CO2 concentrations are at essentially the top of a mountain. This part isn't in the book, but this is the atmospheric CO2 concentrations that's been seen at the Mauna Loa Observatory starting before 1960 and up to the present. And you can see from that one point, no, that's not good. You can see at that one point that there are annual cycles where CO2 concentrations go up, more than likely during the winter, and then during the summer they're drawn down. It has a particular amplitude, but over time, if you average it out, CO2 concentrations have been going up. Well, there's a lot of observatories for CO2 across the globe, and with these we can start to generate what the patterns are of uptake in different parts of the world. I should say that these are the most recent patterns of CO2 concentrations at Mauna Loa. And you can see here we're at 2013, and you can still see these annual cycles that are occurring. And in the winter, essentially, of 2013, we were somewhere close to 397, and probably going to go up a little bit and then come back down and then up a little bit. So CO2 concentrations are still increasing, and there's a seasonal cycle that's pronounced when you take a look at it a little more closely. The amplitude on this cycle, so this right here is roughly 393 down to 384, so only almost 10 parts per million. And if we look here, that's roughly 397, and this is 389, so not quite 10 parts per million, but it's on that order. When we look at a global scale, this is the pattern that we have. So on this axis we have time, so this is year. Here's 2000, here's 2008. On this axis here, we have latitude. So here's the equator, 30 degrees, 6 degrees north, 30 degrees, 60 degrees south. It's a little bit hard to relate the latitude to what we see here, but essentially the equator's roughly there. High northern latitudes there, extreme southern latitudes there. The y-axis is CO2 concentration, starting at a low of 350 all the way up to 400. The pattern to pick up here, so Mauna Loa, I don't remember its exact latitude, but might be somewhere right around here. And that has a seasonal cycle associated with it, just like we saw in the previous figure. As you get closer to the equator, that cycle flattens out, and there's actually not much interannual variation in CO2 concentrations at the equator. So if this is due to seasonality, so in this winter you've got net respiration, in the spring there's still respiration, and then you start to have net negative NEE, so uptake and a lowering of the CO2 concentrations. Once NEE is positive, CO2 concentrations start to increase, and what we saw for an individual point, or could see for an individual ecosystem, we can now see at the global scale. Here, at the equator, NEE is relatively constant over the course of a year. So there's not much seasonality to uptake and loss, and these fluctuations are a lot more damped. When we take a look at the southern hemisphere, the peaks in CO2 concentrations are much lower compared to the troughs, and they're offset from the northern hemisphere. So when the northern hemisphere is releasing CO2, that's when the southern hemisphere tends to be taking up the most CO2. The oscillations are damped because just the amount of land area that you have in the southern hemisphere is a lot less than you do in the northern hemisphere. So with all of this land and all the CO2 uptake that's occurring, you're going to have a lot higher amplitude here than you will in the southern hemisphere. We can take this entire global pattern of CO2 concentrations and start to integrate under the curves. When we do that, we can take a look at factors such as the atmospheric growth of carbon per year. So this is in petagrams of carbon per year, and here's time. And we can see that on average, it's been between 2 and say 4 petagrams of carbon per year. And the atmosphere has been increasing in carbon content over time. Now we can also take a look at the land sink in carbon. Again, here's petagrams of carbon. Here's year on the x-axis. And again, negative numbers here, just like with NEE, represent a sink. And that sink, for all intents and purposes, has been increasing over time. So terrestrial ecosystems are still taking up more carbon than they used to, and that's been increasing. So for these data right here, we're at roughly 4 petagrams of carbon, and it was relatively neutral earlier. Oceans, same general pattern, though there's a lot less variability in the ocean sink than there is in the land sink, mostly due to climatic differences.